towards the north. Okay, so Professor Princess is saying that, oh, as for this one, it will bend towards the normal. So towards the normal. This is R. This is I. So the first law is similar to the first law of reflection, that the incident ray, the reflected ray, sorry, refracted, that's the possibility. The refracted ray, the normal at the point of incidence, all lie in the same plane. Okay, so the similar to what we saw on reflection, the incident ray, the refracted ray, the normal at the point of incidence all lie in the same plane. In fact, from the way it is, you may think it is okay. It doesn't work like that. But you see, if we draw the line, the incident ray, the reflected ray, the normal are all along the vertical plane. Okay, so that's the first law of reflection. Then the second law says that whenever light is propagated from one medium into another. Adelaide, your hand is up.
You said, yeah, is this laws of refraction or reflection?
It's laws of refraction. But the first one is similar to one of the laws of reflection. In that law of reflection, it says that the incident ray, the reflected ray, the normal at the point of incidence all lie in the same plane. This one is saying that the incident ray, the refracted ray, the difference is this. So this is refracted, the other one is reflected. So the incident ray, the refracted ray, the normal at the point of incidence all lie in the same plane. So similar. Adelaide, are you okay?
Yes, please.
Okay. So the second law is saying that whenever light is being propagated from one medium to another, and the densities or the optical densities of the two are not the same, then whenever you take the ratio of the sine of the angle of incidence, sine of the angle of incidence to the sine of the angle of refraction, to the sine of the angle of refraction is constant. So this law is saying that whenever light is moving, travels from two different media, okay, of different densities or optical densities, then the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Okay. And this law This law is what we famously
Steady up.
call as, hello, I'm listening.
Can you repeat yourself? You said something is equal to constants.
So the law is simply saying that whenever light is propagated from one medium into another, and the two media have different optical densities, or their densities are not the same, then whenever you take the sine sin of the angle of incidence, the ratio of the sine of the angle of incidence to the sine of the angle of refraction, this is equal to a constant. This ratio is equal to a constant.
Okay.
And this law is what we call as a Snell's law. Snell's law. Okay. This law is known as a Snell's law. So Snell's law says that whenever light is propagated from one medium into another of different optical density, then the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. Is equal to a constant. If you are writing, please hurry up so we can continue. Are you done? Hello, are we done?
Yes, please.
Okay. Before I explain Snell's law into details, please let me chip in something important. We have what we call as the reversibility of light. Reversibility of light. Let me write what I'm saying before I come back to Snell's law, okay? So I'm talking about reversibility of light. You see, whenever light, if this is air and this is glass, and it is propagated from a less dense medium into a denser medium, it will be refracted towards the normal angle of incidence, angle of refraction. When you reverse the source of light and then bring the source here, if we bring the source of light here, okay, and then we give it this same angle of refraction. Now we are looking at the angle of refraction R as the incidence from glass to air. Before it was air to glass. So when we pick it from here, it will take the same path as the incident ray. It will take the same path, okay, and this will now behave like the refracted ray. Okay, the arrow here will behave like the refracted ray. Now it also give us the same angle of um the same angle of incidence then will be equal to the angle of refraction now. It will take the same path so long as you give it the same angle of incidence as the angle of refraction, and then it will also give you the same angle of refraction as the then angle of incidence. And this is what we term as the reversibility of light. Meaning, if you are moving from here to here, whatever you get will be the same as when you are moving from here to this part. Please, are we fine? Are we okay?
Area.
Hello, princess.
So are you saying that the mag like nothing won't change? So let's say it
Yeah,
won't bend.
nothing will change. It will take the same path.
Okay.
So let me give you something to put down on reversibility of light. Are you ready? So the principle of reversibility of light, the principle of reversibility of light states that if light after suffering, any number of reflections and refractions, it applies to both reflections and refractions. If light, after suffering any number of reflections and refractions, has its final path reversed, has its final path reversed, it travels back, it travels back along the same path. It travels back along the same path in the opposite direction. If light, after suffering any number of reflections and refractions, has its final path reversed, has its final path reversed, it travels back along the same path in the opposite direction. Okay, it travels back along the same path in the opposite direction. So if it's about reflection, this is how it will look like. We have a mirror coated. So if this is the incident light, when it hits it, it will reflect. Okay. Now when you bring the source here, this is the source. The source is here. If you change, let me bring the normal. Angle of incidence, angle of reflection, R. If we change the source and then bring it here, when we are giving it this same angle as the angle of incidence, now this will be the angle of reflection. It will take, so long as it's about the same angle, it will take the same path. For instance, it will never change and then reflect along the same path. It will never change so long as we are not changing this. Are you okay? That is the principle of reversibility of light. Any question? Okay. So let's go back to the second principle, Snell's law. The second law, rather. So whenever you have two media of different optical density. Boundary, the normal, incident ray, refracted ray. This is the boundary, air to glass. It can be boundary, normal. This is glass, air, incident ray, refracted ray. All that Snell is saying is that in both cases, when you take here, when you take the ratio of the sine of the angle of incidence to the sine of the angle of refraction is equal to a constant. When you come here, sine I over sine R is equal to a constant. And this is what we call as Snell's law. Snell's law. Please do not also forget that the principle of reversibility also happens here. When you reverse the part this way, when you reverse the part this way, or the direction of it will take the same path in both cases. So the principle of reversibility also occur here. Are we okay? Are we okay?
Yes.
Okay. Now, this constant value K is what we call as the refractive index of the material, represented by the symbol mu or nu.
Hysteria.
Hello.
Hysteria, please.
The late case.
The arrows. Mister. Hysteria, please. The arrows have changed, but then the angle of incidence and the angle of refraction, they are the same.
Because you just joined us. All that we are changing is the source. Before the source was here. Okay. And then there's the emergent ray coming out of the second medium. Now we are reversing it by taking the same angle, but the source is now here. Source of light is now here. Meaning we are taking this R value as the angle of incidence. Okay. So long as we are taking the same part and the same value of R, it will also take the same part to come out from the air medium. So this time, this will be the emergent ray. Okay. And that explains the principle of reversibility. I talked about that, but because you just joined us, that's why. Okay.
Yes, please.
All right. Now, what does it mean by Snell's law? Snell's law, what does it actually mean? It simply means that, let's take light coming from air to glass. Air to glass. So the path is actually from air to glass. Angle of incidence, angle of refraction. So I here, R here. This is the incident ray. This is the refracted ray. Now I'm going to pick some values of I. Every I would give me a corresponding R. So I and then R. So let me assume to start by increasing I from maybe 10, 20, 30, 40, 50. Now every I we take would have to give us a corresponding angle of refraction. This is a practical thing we are doing. We'll do a lot of practicals on this. So every I would give us a corresponding R. But my question is that as I increases, what do you think will happen to R?
R will decrease.
Okay. So we'll have, because R is, once it is added to glass, it will be deviated to the normal. Okay. It will be, so as you increase this, okay, it will still be deviating towards the normal. So let's assume this I gives us 50. Then 20 would give us maybe 45, 40, 35, 30. In fact, I am just assuming values, but I just want you to understand that I will be decreasing. So this is increasing, this is decreasing. Are we okay? Are we okay?
Yes, please.
I'm just creating values. Now, whenever I take sign of I and take the sign of R, so sign 10, sign 20, sign 30, sign 40, these are values that I'll be recording here. Then sign R, which is the sign of 50, 45, 40, 35, 30, on and on. When I take the ratio of sign I on sign R, it should give me a certain value, which I'm calling as a constant. Meaning, so long as every I goes with R, its corresponding R, okay, the ratio of the sign of this one, which I'll record here, to the sign of this one, which I'll record here. When I find it, it should give me maybe a certain value. Example, 0.52 something. I don't want to point because these are values that I guess. Okay, it may not be right. That's why I'm not actually inputting the value. But I'm assuming after taking the sign of this, this gave me 0.5 something, 5, maybe 4. If I take the sign of this value, which I'll record here, the sign of R, which is this, which I'll also record here. When I take the ratio, sine I over I, it should also give me a value 0.5, maybe 39 something. If I take the sign of this, 30, then the sign of 40, which I recorded, and then divide this by this, it should also give me a value 0.5, maybe 499 something. Okay, in each ratio, the value should be the same or very, very close. So each sign I and sign R should give, in each situation, must give us a constant value. So long as it's the same first medium and then the second medium. Whenever you find the ratio of sine I and sine R, it should give you a constant value. So the values that I'll be recording in each case must be so the same or so close. That is what we mean by the Snell's law. Please, are we okay?
Miss Stadia, can you please go?
Okay. I'm checking roll call at the same time, so I'm coming in. Okay. All right. So let's assume, even though I fabricated this, but let's assume, please help me find sine 10. What is sine 10? Give me your answer in 3dp, sine 10. And somebody should also calculate sine 50. Make sure your angular measurement is in degree.
0.174.
0.174. And then sine 50. Sine 50.
0.766.
0.766. Sine 20.
0.342.
0.342. Sine 45.
0.707.
Sine 30. 0.5500. This is sine 30 is my friend. Sine 40.
0.643.
0.643. Sine okay, so sine 40 again. Okay, so 0. Sine 35.
0.574.
Sine 50.
0.766.
And then okay, so let's divide sine R I by sine R. So 0.174. Somebody should also pick the other one. Okay. So if you're going to start with 0.174, divide by this. Let's see what it will give us. This is giving me somewhere 0.2227. If you forgot, is that what you got? Here, please, Akofala and the rest of you should also help out. Oh, Brittany, your line is breaking. Oh, so Akofala, are you there?
Yes, please.
Oh, and you are not helping me. Oh, your mother will hear. Oh.
1.12.
And the last one, Evia Bogwa, where are you?
Stadium here.
And you are quiet.
My
Okay.
network was
Okay. So you see, in actual practical situation, this because these are values I guess. Okay, I guess this, that. When you in actual practical work at the laboratory, whenever you choose this I and determine the corresponding R, and you find this, and you take the ratio of I, and this must give you answers that are very, very close, either the same or so close. Okay, it will not be like this. And that is what we mean, that the sign of the ratio of the sign of I to the sign of R must be equal to a constant. This value must be constant. So let's assume this can be maybe 1.10011. Okay, this is 1.1002. This is 1.001. And look at these values. Look at these modified values. They are almost the same. And so I can say that this is in actual sense. In fact, it will be 1 point, if this is 1.5, then this will be around 1.499. This will also be